Good day, everyone. Today, we are going to present a very timely and relevant topic entitled Biodegradable Plastics from Carbohydrate-Based Polymers, Innovations and Environmental Impacts. In this presentation, we will discuss how carbohydrate-based materials are used in producing biodegradable plastics, an eco-friendly solution that may help reduce plastic pollution and benefit the environmental in the long run. But before we begin, let me first introduce to you the members of our group. So first, we have Kayla Roshana, followed by Kiandra Soor, and lastly, Franz Bonifacio. And I am Shalame Pialgor Wallace, your presenter for this part of the discussion. We are from Group 7 from Section B, and together we prepared this presentation to give you insights on this innovative and environmentally significant topic. Introduction. This study explores the potential of carbohydrate-based polymers such as starch, cellulose, and chitosan as biodegradable alternatives to petroleum-based plastics. With global plastic pollution worsening, these renewable materials offer an eco-friendly solution by reducing carbon emissions and supporting sustainable practices. The research examines their environmental impacts, biodegradability, and practical applications aiming to contribute to the shift toward greener material innovations. This research investigates starch, cellulose, and chitosan as eco-friendly replacements for traditional plastics. These renewable materials offer a biodegradable solution to reduce pollution and promote sustainability. The study focuses on their environmental impact, how easily they break down, and their potential uses. The goal is to help create more environmentally friendly plastic alternatives.
Good day, everyone. I am Kayla Roshana, your second presenter. Research Gap. The ongoing global crisis of plastic pollution presents both an environmental challenge and an urgent call for innovation in material science. Despite the proliferation of biodegradable plastics, a significant gap remains in understanding the ecological trade-offs, long-term performance, and policy implication of carbohydrate-based alternatives. As argued by Thompson and Woodward 2023, current literature tends to focus on individual polymer types without a comprehensive evaluation of their environmental interaction or biodegradation kinetics in various ecosystems. So, the efficacy of biodegradable plastic as a sustainable alternative to conventional plastics remain a subject of ongoing investigation. While offering a promising solution to the global plastic pollution crisis, a comprehensive understanding of their environmental impact is lacking. Current literature predominantly focuses on individual polymer characteristics, neglecting a holistic assessment of their life cycle and interactions within complex ecosystems. This necessitates further research into several critical areas. First, the ecological trade-off associated with their production and decomposition pathways, including potential negative consequences such as the release of harmful byproducts or alteration of soil properties. Second, the long-term performance and degradation kinetics under diverse environmental conditions, considering factors such as temperature, humidity, and microbial activity. And third, the policy implications of incomplete data for effective waste management strategies and the development of robust regulatory frameworks. A systems-level approach encompassing the entire life cycle from synthesis to ultimate fate is crucial for a rigorous evaluation of the sustainability of biodegradable plastics and the development of truly environmentally benign alternatives.
Moving on to the objectives of our research. First objective, to explore how bioplastics can help reduce plastic pollution. We selected this objective because plastic pollution remains a major environmental problem worldwide. Most plastics used today are petroleum-based and take hundreds of years to degrade, causing harm to ecosystems, marine life, and even human health. By investigating how carbohydrate-based bioplastics degrade naturally, we want to see if these materials can reduce waste accumulation and environmental damage compared to traditional plastics. This is an essential step toward finding sustainable solutions to pollution. Second objective, to assess the environmental impacts of using carbohydrate-based biodegradable plastics compared to conventional petroleum-based plastics. This objective was addressed to ensure that switching to biodegradable plastics does not create other hidden problems. For example, while a material may decompose faster, its production process could be energy intensive or require harmful chemicals, making it less eco-friendly overall. Through this comparison, we can properly evaluate if carbohydrate-based plastics are truly better for the environment throughout their entire life cycle from manufacturing to disposal. Third objective, to compare carbohydrate-based plastics with regular plastics in terms of usage. It is not enough for a material to be biodegradable. It must also be useful, durable, and efficient in various applications such as packaging, agriculture, and medical devices. This objective ensures that these bioplastics are practical substitutes that can meet the same performance standards as petroleum-based plastics in daily life or industry use. Without this, industries may hesitate to adopt the new material. Fourth objective, to identify common examples of biodegradable plastics made from carbohydrates. By fulfilling this objective, we provide concrete real-world examples that show how this technology is already being used or developed globally. These examples can inspire industries, researchers, and even consumers to support or shift towards biodegradable options. Without identifying this, the study would remain theoretical and disconnected from what's happening in actual markets and industries. In conclusion, these four objectives are interconnected and necessary to fully assess the potential of carbohydrate-based biodegradable plastics, not only as an environmental solution, but also as a practical, effective, and sustainable alternative to traditional plastics.
Discussion and analysis. Number 1. Role of biodegradable plastics in reducing plastic pollution. Overview of plastic waste management and sustainability. So the main challenges identified is number 1 is high rate of plastic pollution. 79% of plastic end up in landfills or nature instead of being properly management or recycled. And also number 2 challenges is microplastics, contaminations, and toxic. And number 3 is limited effectiveness of biodegradable. And number 4 is a poor waste management system. And number 5 is public misconceptions. And also number 6, lack of policies and infrastructure. So addressing these issues requires systematic efforts involving government's actions and also technological infrastructure and public education. How carbohydrates-based plastics contribute to minimize environmental harm. So carbohydrate-based plastics helps minimize environmental harm by using a renewable resource and being biodegradable or compostable, and also reducing carbon emissions and producing less toxic waste. They are greener alternative to conventional plastics, especially when used responsibly and supported by proper waste management system. Environmental impact of carbohydrates-based bioplastic versus conventional plastic. So, comparative of biodegradation rates and decomposition efficiency. Carbohydrates-based bioplastics degrade more efficiency than traditional plastics, but only under the right conditions, such as industrial decomposting or etc. Their environmental benefits are clear, but successful implementation depend on waste management system, public understanding, and proper disposal practices. Carbon footprint and life cycle assessment of bioplastic versus petroleum-based plastic. So carbohydrate-based bioplastics have a lower carbon footprint than petroleum-based plastics and are more sustainable over their life cycle, but their successful depends on proper disposal system, responsible sourcing of raw materials, supportive policies, and public awareness. So those realizing their full environmental benefits requires both technological infrastructure and informed consumer behavior. Effects on marine and terrestrial ecosystem, including microplastic reduction. So to mitigate these impacts, a holistic approach is needed. One is innovation, develop more biodegradable and eco-friendly materials. Two is restoration, clean up polluted ecosystems, and sustainable practices like reducing plastic use, improve waste management, and encourage recycling and composting. So the number 3 topic is a functional comparison. Carbohydrate-based versus petroleum-based plastic. So strength, flexibility, and durability of carbohydrates-based plastics in real-world application. So carbohydrate-based are: one is eco-friendly, number 2 is good for short-term disposable products. So not strong or durable enough for demanding application. Challenge and limitation in widespread adoption. So carbohydrate-based bioplastics are promising but face technical, economic, and systematic obstacles. Overcoming this will require coordinate efforts across science, policies, industry, and public education. Feasibility and cost effectiveness of bioplastic for industrial use. So carbohydrate-based bioplastics hold promise for industrial use, but their current high cost, limited scalability, and resource competitions and are major hurdles. Addressing this will require coordinates efforts in technology, infrastructure, and policy. So the number 4 topic is a notable example of carbohydrates-based biodegradable plastics. Overview of starch-based, cellulose-based, and chitosan-based plastics. All three types needs specialized processing or adaptive boost to their performance, while their low grades promise for sustainable plastic alternatives. Continued innovations is crucial to expand their use in an industrial commercial application. So, application in packaging, agriculture, and medical fields in base bioplastic. So, this focus on using alternative feedstocks, more sustainable raw materials, and also enhancing biodegradations and functionality, improve manufacturing techniques. So these goals aim to boost performance, reducing costs, and supports cellular bioeconomy and economic model based on sustainable regenerative practices.
So, summary of findings. First, recap of how biodegradable plastic can address plastic pollution. Carbohydrate-based biodegradable plastic sourced from starch, cellulose, and chitosan offer significant promise in reducing plastic pollution by decomposing faster than petroleum-based plastic. Their biodegradability under industrial composting condition makes them suitable for short-life applications. However, their environmental benefits are highly dependent on proper waste management systems, particularly composting infrastructure and public awareness of correct disposal practices. Second, summary of environmental impacts of carbohydrate-based biodegradable plastics. Compared to conventional plastics, carbohydrate-based bioplastics generally have lower carbon footprints and reduce energy demands during production. They release fewer greenhouse gases and do not emit harmful toxin during degradation. However, their environmental performance is context dependent. While they degrade effectively in compost and soil, they break down much more slowly in aquatic and landfill conditions, highlighting the need of integrated waste strategies. Third is overview of performance comparisons between biodegradable and petroleum-based plastics. Although eco-friendly, carbohydrate-based plastics typically exhibit lower mechanical strength, thermal resistance, and moisture stability than petroleum-based alternatives. This limitation currently restricts their use in high durability or long-term applications. Nonetheless, advancements in material science such as blending with nanomaterial and biopolymer reinforcement are improving their flexibility and resilience, extending their functional reach. Fourth is identification of common carbohydrate-based biodegradable plastic examples. Notable examples include starch-based films for compostable food packaging, cellulose-based derivatives for biomedical devices and burial applications, and cytosine-based materials for antimicrobial films and wound dressing. These bioplastics are already being adopted across packaging, agriculture, and healthcare sectors, where biodegradability and safety are prioritized. 5 is adoption barriers and industrial viability. Technical constraints, production cost, limited infrastructure, and consumer confusion continue to challenge the mainstream adoption of carbohydrate-based bioplastics. Without improvements in manufacturing efficiency and stronger policies to support composting and eco-labeling, the full sustainability potential of this material remains unrealized. 6 is outlook for innovation and sustainable integration. Future research is focused on expanding feedstock sources like algae and agricultural waste and optimizing biodegradability under diverse environmental conditions. Emerging production techniques such as microbial fermentation and additive manufacturing are enhancing performance and cost effectiveness. Paired with supportive regulation and public education, this innovation can drive broader adoption and help align bioplastics with global sustainability goals.
Conclusion. This study concluded that carbohydrate-based biodegradable plastics made from renewable sources like starch, cellulose, and cytosine, and promising alternatives to petroleum-based plastics due to their lower carbon emissions and ability to degrade safely. However, their adoption is limited by weak mechanical performance, high production costs, and public misconceptions. Continued innovation in material designs combined with improved infrastructure and policies is essential for these bioplastics to support a sustainable and circular economy. The study also found that plastic made from things like starch and cellulose instead of oil are good replacement for their regular plastics because they produce less pollution and break down safely. They are not also used much because they are not strong enough, are expensive to make, and people have some wrong ideas about them to make these better plastics more common we need to improve how they are made and create better policies to support them. Recommendations. Based on the findings of this study, the following recommendations are proposed to support the effective development, adoptions, and impact of carbohydrate-based biodegradable plastics. First, strengthen waste management and composting infrastructure. This to maximize the environmental benefits of carbohydrate-based bioplastics. Governments and municipalities should invest in expanding industrial composting facilities. Infrastructure upgrades should include standardized collection systems, clear waste stream separation, and post-consumer compost validation. Second, enhance public education and eco-labeling standards. This to clear distinctions between biodegradable, bio-based, and compostable plastics should be emphasized through standardized labeling and public awareness campaigns. Education initiatives should focus on promoting responsible disposal behaviors and reducing contamination in organic waste streams. Third, promote material innovation through research and development. This to continue R&D is essential to improve the mechanical strength, thermal stability, and moisture resistance of carbohydrate-based plastic, encouraging interdisciplinary collaboration between material scientists, chemical engineering, and biotechnologies will accelerate the development of high-performance formulations suitable for diverse applications. Fourth, scale up the use of agricultural residues and non-biomass. This to ensure sustainability and reduce competition with food systems. Bioplastic production should prioritize feedstock such as agricultural waste, lignocellulosic biomass, and algal sources. Government incentives and private investment can support biorefineries focused on converting this feedstock into high-value polymer precursors. Fifth, support industrial adoption to policy and incentives. This to make policymakers should implement subsidies, green procurement mandates, and tax incentives to lower the economic barriers associated with bioplastic manufacturing. Standard and certifications should be established to ensure product consistency, performance, and environmental compliance. 6. Foster international collaboration and regulatory harmonization. This to addressing plastic pollution is a global challenge. Collaborative research, shared best practices, and harmonized regulations across countries can promote the widespread adoption of biodegradable plastics and prevent fragmented progress. And lastly, 7th, monitor environmental outcomes through long-term life cycle analysis. This to ensure that biodegradable plastics deliver on their sustainability promise. Ongoing life cycle assessment should be conducted across various environments. This assessment should inform future design improvements and guide regulatory updates performance data.
Before we formally end this presentation, we would like to take this moment to sincerely express our gratitude to the people who have made this research paper and oral defense possible and successful. So first and above all, to our Almighty God for granting us the strength, knowledge, and guidance throughout this research journey. And most especially to Ma'am Mel, our research advisor and subject instructor, who patiently guided and corrected us from the beginning of our manuscript writing until the finalization of this presentation. She gave her time, effort, and expertise to ensure that every part of our research, from the flow of ideas, content development, and even up to our PowerPoint and oral delivery, would met the best possible standard. So her dedication, corrections, and suggestions greatly helped us improve and perfect our work. So without her consistent support and guidance, this output would not have been as organized, clear, and meaningful as it is now. We are also thankful to our classmates and friends for their motivation and encouragement throughout this process. Once again, from all of us, thank you very much, Ma'am Mel, for being a great mentor and guide in this journey, and to everyone who became part of this success.